All right, guys. So I'm going to give you some stoichiometry notes via a video. So for gas stoichiometry, we are dealing with gases and stoichiometry. So these are reactions that involve gases. And there's two different types of gas stoichiometry questions. So our first type and our easier type is when something is at STP, right? And so put a big smiley face. That makes that a lot easier because we know that at STP, that 1 mole of any gas occupies 22.4 liters, right? And so when you can use 22.4 liters, you can just stick that in a T-chart, and that makes it very, very simple. So for example, if I have, let's just use propane because it's very easy. C3H8 reacts with 5 moles of oxygen to produce 3 moles of carbon dioxide and 4 moles of water, right? So in this reaction, let's just say if I had 187.2 grams of propane, what would be the volume of CO2 produced at STP? And so because you're at STP and you can use 22.4, all you have to do is set up your T-chart. Starting with your given, 187.2 grams of C3H8. C3H8 grams will cancel, and that will go to 1 mole of C3H8. And then for every mole of C3H8, I produce 3 moles of carbon dioxide. There's a 3, right? And that's from the balanced equation. And then every mole of carbon dioxide, and I want the volume of CO2. So C3H8, when I add those together, is 44 grams per mole, and then my liters is 22.4, right? And so I know in my handy dandy calculator that 187.2 divided by 44 times 3 and then times 22.4 makes 285.9 liters of carbon dioxide, right? And so we've been doing this, and so this isn't hard. This is something you've been practicing. The problem that arises is how many times are you making a burger at the beach while it's snowing, right? So the temperature would be 0 degrees Celsius in that scenario. I'm going to say not very often, right? And so really gas stoic is going to happen at non-STP conditions. When I change my pressure and my temperature and I'm not at standard pressure and temperature, not that it's really, really sad, however, it is more complicated. And it's only more complicated in that you can't use 22.4 liters. Everywhere where you would have used 22.4, you have to use PV equals nRT. You've got to use the ideal gas law. Right? So every time you feel like you would use that, you can't. You've got to use PV equals nRT. So we're going to work out this exact, well, not this exact same problem. Let's change up the problem a little bit. We're going to use the same equation. How about that? So let's say what volume of carbon dioxide can be made from, let's start with like 58.2 grams of propane at, right, we live in the mountains, we're a little less than 1 atmosphere, let's go 0.0979 atmospheres. And it's not 0 degrees outside. It was almost 70 the other day. Ooh, crazy. So let's make it 27 degrees Celsius outside. A nice warm day to grill a burger. Okay, so in this scenario, right, I've got grams of propane and I want volume of CO2. So because I'm again changing substances, I still have to go through my mole ratio. I just don't want this last box. So I'm going to stop at moles of CO2 and then plug those moles in for my N equals nRT, right? And then I can solve for the volume by dividing by the pressure. So I'm going to still start this problem the same way, 58.2 grams of C3H8. Mass will go into a T-chart every single time. And that still weighs 44 grams of propane in 1 mole. And they are still in a 1 to 3 mole ratio. So for every mole of propane, we make 3 moles of carbon dioxide. But I need to stop here because I can't find volume. I've got to plug my moles into PV equals nRT. So 58.2 divided by 44 times 3 is 3.97 moles of carbon dioxide. And now to find the volume of carbon dioxide, PV equals nRT, and I'm going to divide by pressure on both sides. And so my moles times my R, 27 plus 273 is a nice even 300 Kelvin divided by 0.979 atmospheres. So 3.97 times R times T divided by P is 99.9 liters of CO2. Okay. That's not the only scenario, right? So that's a grams going to volume. Let's do another example where we go backwards. Okay. So if I know the volume of something and then I wanted to find the grams, right? So let's say what mass of water, we're still using the same equation, the propane equation, what mass of water is made from, let's just go 80 liters of oxygen, but not at STP, right? We're going to make these non-STP conditions. Let's increase the pressure this time. Let's go to 1.21 atmospheres and 16 degrees Celsius. Okay, so here I want to find the mass of water. Okay, so I can't start with a T-chart because I'm starting with a volume, a pressure, and a temperature. So because I've got my V, P, and T, in this scenario, to get the mass, I'm going to have to first do PV equals nRT, solving for the moles of oxygen, right? Liters of oxygen, we'll go to moles of oxygen, and then using those moles of oxygen in a T-chart to then find the mass of water. So in this scenario, PV equals nRT. I'm going to divide by RT on both sides to solve for moles. So my pressure is 1.12. My volume is 80 liters. My R is 0.821. And my T, 16 plus 273 is 289. Because this is the volume of oxygen, what I'm solving for is moles of oxygen, okay? So 1.21 times 80 divided by 0.0821 and divided by 289 is 4.08 moles of oxygen, okay? Now that I have moles and I want mass, I simply get to put this into a T-chart. I'm going to get from moles of oxygen. I can only go from moles of one thing to moles of another thing using a mole ratio. Oxygen is in a 5 to 4 mole ratio with water in our propane equation. And then 1 mole of oxygen, nope, water. 1 mole of water cancels, and I want mass of water, and water weighs 18 grams per mole. Okay, so my 4.08 times 4 divided by 5 times 18 is 58.7 grams of water. Okay? The worst one when it comes to non-STP conditions is when I don't give you a mass at all. Because instead of doing any T-charts, you simply would have to do PV equals nRT, convert those moles of whatever volume you have to moles of what you wanted using your mole ratio, then plugging those moles back into PV equals nRT. That's the longest way to do that. I will do one example of that because I think you do need to see it. So I'm going to flip this sheet over. And let's change up our equation just to make it different. So let's say we've got nitrogen reacting with 3 moles of hydrogen producing 2 moles of ammonia, right? So in this scenario, all 3 of these things are gases, which is helpful in gas stoichiometry. Okay. So with these, we're going to have, let's say, what volume of hydrogen is needed to react with 50 liters of nitrogen at 0.821 atmospheres and 30 degrees Celsius. Okay, so again, I'm not given anything that can go into a T-chart. At non-STP conditions, when I see a volume, a pressure, and a temperature, the first thing you need to think of is PV equals nRT. I'm going to solve for moles, so I'm going to divide by R and T on both sides. So my moles are going to be my pressure times my volume divided by R, and 273 plus 30 is 303 Kelvin. Using my handy dandy calculator, 0.821 times 50 divided by 0.0821 divided by 303 is 1.65 moles. But here it's really important to keep track of what substance you have. So because this was nitrogen, this is nitrogen. Okay, you don't randomly solve for moles of something else using PV equals nRT. You're just converting that volume into moles of the same substance. Okay, to change substances, you have to use a mole ratio. So 1.65 moles of nitrogen is in a 1 to 3 mole ratio with hydrogen. So 1.65 times 3, right, is 4.95 moles of hydrogen that you're going to be reacting stoichiometrically with that nitrogen. But then I don't want moles, right? I want volume. So because I want volume, this is going to go back into PV equals nRT. Solving for volume means I'm going to divide by pressure on both sides. I'm going to use my moles of hydrogen, my R, and my T, divided by my pressure. And you get 140 9.985. This does kind of screw up our 3 sig figs. Got 3 sig figs. To just be 150 decimal liters of hydrogen gas to get my 3 sig figs. I hope that was helpful. If you have questions, please ask. I'm here.